Hello once again. This video is a continuation of our series regarding data representation using binary numbers. In the last video, I've shown you how to convert decimal values into uh, floating point representation. Earlier, I also have uh, shown you how to convert it into a format called fixed point format. In this video, I'm going to compare the floating point format with the fixed point format and explain why the floating point format is now the dominant format for representing fractional values in computer. I'm going to use my earlier conversion of the value 35.62 into floating point format. Remember that earlier we have computed the the exponent and the mantissa of 35.62, and we have determined that the actual representation is 00110 for the exponent and 100111001 for the mantissa. In this example, we are going to convert 35.62 into fixed point representation using the same pick and mark method. In this case, we will need the values of 1, 1, 1, 2, 4, 8, 16, and let's move this one more, and 32, because 35 is greater than 32. And then I will copy the first 6 columns of the table that we use to convert fractional values. To make a long story short, now let me adjust the columns to be able to show all of them, and then let me copy the formulas. Okay, let me just copy the formulas so it will be easy. And our decimal position, we will fill up our decimal position with the color red to indicate that this is the position of our binary point. And we will transfer the value that we need to compute here. We will copy the same formula here. Let's just change the formula, make sure we have the right one. Okay, so now we'll start up picking and marking. The first mark is 32. We have 3. The next mark is 2. The next mark is 1. The next mark is 0.5. And with 0.12, we cannot mark this. We can use this. And we cannot use this. And we can use this. And we will mark the uh, vacant values with 1, with 0. So our equivalent is 1. We'll have 1 0 here. Our equivalent is 1 0 0 0 1 1 1 point 1 0 1 0 0 1 0 1. Okay, so this is our fixed point equivalent. Now, take note that uh, we have we can extend this to 15 bits because there's currently 1, 2, 3, 4, 5, 6 by including 3 zeros. Okay. So we have now 15 bits, the same as our fixed point representation, which is also 15 bits. Now, what's the difference now? Look at the residue of the floating point and the residue of the fixed point. We compare the values. These are the last remainders of the conversion process. We can say that the residue of the fixed point representation is magnitudes bigger than the residue of the uh, floating point representation. This proves the point that floating point is more precise, which means that it has a more exact conversion of a decimal value compared to fixed point. To illustrate this point further, let us convert uh, the value uh, uh, the value 70. If we convert the value 70 using the same table in floating point format, we cannot convert it into floating point because we need another bit. However, we can use the same set of bits without expanding for the exponent or for the floating point conversion. For example, we have 70, so we'll just continuously divide this by 2. Copy, replace values, and we copy this again, place values, paste values, until we do this process until we reach 0, during which we will start converting our exponent and our mantissa. Paste values. So now we will count our divisions. 7. So our exponent here is 7, and our mantissa will be converted. Our exponent is 7, so we will have 0, 1, 1, 1. And our mantissa is this. So we will convert this again using the same process that we did for our previous mantissa, using the same 10-bit format. And we'll just erase. I will start picking. We'll have 1, 0, 4. So we are up to this. And can we mark this? No, so we are up to this. And then 0.015, we can mark this. So we now have an exact conversion. We don't even need 10 bits, but we only need 6 bits in this example. Okay. So our mantissa is 1, 3 zeros, followed by 2 ones, followed by 4 zeros. This is an exact conversion. Now, in our example, we cannot use fixed point to represent the same value without extending one bit. And we will do that to show the point. So our equivalent, okay, we will have to extend this to 54, and we'll have to copy this. We'll have 70. We'll have to sum this. And let's remove our mark. And then we will subtract our running and mark this as red or running different. So we mark 64. We're left with 6. We're left with 2. And we're left with 0. So we are able to convert this to the value 70. But this time, we are adding an additional bit. That's one of the disadvantages of the fixed point representation. In the other example, we did not add any bit to our format for floating point, but still it was able to convert the value 70 exactly. So that's another advantage of the fixed point of the floating point representation over the fixed point representation. There are certain values that can still be represented by fixed point without expanding its number of bits, by floating point without expanding its number of bits, while the fixed point representation may need to expand its number of bits. And on the other hand, the residue, the final residue of the floating point representation is magnitudes smaller than the final residue of the fixed point representation, which says that floating point is more precise than fixed point representation. I hope you see the point behind this, why floating point representation is now the popular format used by computers. In the next video, I'm going to show you how to add binary numbers both in the fixed point and floating point format. Bye for now and see you in the next video.